Hello, and welcome to our first installment of Mathematical Foundations of Physics, number 1. And that title of it is Numbers. The main things that we want to take away to know from this lesson are contained right here in this box. And ultimately, by the end of this episode, this episode, you should have a sense of what we need to know about numbers in physics. So the first thing we need to know is that there are two types of numbers, discrete and continuous. And that's probably new terminology for you. In mathematics classes, we're more often concerned with whether something is an integer or a real or an imaginary or a rational or an irrational number. We're not really concerned with those kinds of labels in physics. But this idea of whether numbers are discrete and continuous, we are concerned about. The second thing that we have not probably spent much time thinking about up until now is what numbers mean. And in physics, what numbers mean depends on where they come from. And there are 5 different places that we will go in depth that numbers can come from. So the numbers themselves can be counts, they can be mathematical constants, they can be measurements, they can be the result of a calculation, or they can be an estimate. And every one of those types of numbers, where it comes from, has a big effect on how we treat it in mathematics. And thirdly, we have a convention for communication that we want to use when it comes to numbers, and that is that we have no naked decimals. That means when we write a decimal number, we always put a 0 in front of it, not just simply a decimal point, 0.55. There are a number of reasons for that, but you'll notice when you type a number into a Google Sheet, it will always put that 0 in there, and there's a reason for that. The simplest one is that that's just something we all agree to do in science. But secondly, why we agree to do that is because it's easy to miss that decimal point. So we put the 0 there to draw our attention that it is a decimal. So what I'd like you to do at this point is to just, you might want to pause the video for a few seconds and read these 2 paragraphs on about discrete and continuous numbers. And when you're done reading that, we'll discuss it. So now you're back from having read a little bit about discrete and continuous numbers. So what I want to do here is just point out the elements that I would draw attention to. So discrete numbers are countable, things that you can count. They are distinct and separable. The examples won't be so helpful to us in terms of our purpose with physics. But the important thing here is that discrete is in contrast to continuous mathematics and continuous numbers. And that means they can range in value over all the real numbers. And the next distinction I would like us to make is that since Isaac Newton, most of the physics we're going to begin using, almost the entire emphasis has been on continuously varying processes. Infinitely subdivisible, continuously varying. In contrast, discrete mathematics with finite collections of discrete objects. And it turns out that around 1900, the vast implications of this really came to the fore in physics, and those where we ascribe a lot of things to Einstein, but around that time, the immediate decades before, and since then, our whole view of the nature of the universe has changed, and it has to do with the nature of continuous versus discrete. So let me illustrate by example what we mean by continuous versus discrete. So discrete things are, they're like integers. There's only distinct values, but they're not really just limited to integers. They can be any kind of number, rational or irrational or imaginary, etc., that has a definite value of a definite size. Whereas continuous numbers are infinitely subdivisible. So let's illustrate this here a little further. We could take a look at, say, eggs. Those are things we can count. There are either 1, 2, 3, 4, or some number of eggs, but there cannot be 0.6 eggs or 0.65 eggs or 0.72 eggs. So let's take this example a little bit further. What might we look at for a continuous example here? You could take any number of eggs and you can scramble them. And then after you've scrambled them, you can take any amount of those scrambled eggs, any decimal portion, any fractional portion that you'd like. So whereas an egg itself is discrete, scrambled eggs are continuous. So again, something that's discrete can be counted. It's a whole number multiple of an exact number. It doesn't have to be a whole number, but it has to be a whole number multiple of an exact number. Continuous things can't be counted. They must be measured by comparison to some standard. Now, that's actually the definition of what measurement is. It's examining an attribute of something compared to a standard. But continuous things can't be counted. Now, you may have noticed or not have noticed, in some grocery stores, you'll get to the checkout line, and some of them will say 10 items or less, and other stores will say 10 items or fewer. It turns out those two words, less and fewer, highlight grammatically the difference between discrete and continuous concepts. See, less is an amount. Fewer is a number. So it turns out to say 12 items or fewer is correct. It's incorrect to say 12 items or less. Just as you could say that a class has 12 students or fewer, it would be incorrect to say you have 12 students or less. And so there's that manifest use of that language in classrooms. It turns out, for what it's worth, most grocery stores do it incorrectly. They'll say 10 items or less. Turns out the more highbrow the grocery store, the more likely it is that they will do it grammatically correct. So let me give you another example. Some objects can have a character of being both continuous and discrete. Both discrete and continuous. And whenever that happens, when we seem to have these opposite qualities, but yet something can display both of them seemingly in a way that should be impossible, we call that duality. So let's take an example of a cement block. On the one hand, you can only purchase blocks, whole blocks. You can buy 1, 2, 3, 4, 5, or 6. On the other hand, you can break that block down into pieces of nearly any fraction of a whole block. So in a very loose sense, a cement block just shows a duality of whether it is continuous or discrete. So let's talk a little bit more about the sources of numbers and where they come from. Up until now, probably in your education, a number is a number is a number is a number, whether it's a measurement or a count or anything like that. So we have already spoken about what counts are. Those things are exact. As such, they have infinite precision, which means they have infinite number of significant digits. If someone said they counted 4 dogs, that number 4 for the 4 dogs has infinite precision. The number of significant digits is infinity. There is no uncertainty about that number. So 4 in this case has an infinite number of significant digits. And although the concept of significant digits you were introduced to in chemistry, you didn't come across this way of looking at significant digits. And you will see throughout the course, or we'll focus on this all year, why this is important. The second type source of numbers are mathematical constants. Those things are exact. They also have infinite precision and infinite number of significant digits. So let's take, for example, the formula that we all know and love, the formula of a triangle. There is one number located inside this formula, and it is the number 1/2. And so if I were to ask, how many significant digits are there in that ratio 1/2? It might give you pause, you might scratch your head, and you might rest on the answer 1. But looking at that a little more closely, we can ask ourselves, this 1, how sure are we that it's 1? Could it be 0.9? Could it be 1.1? And this 2, could it be 2.1 or 1.9? And the answer is no. There is no chance that this number is anything other than 1. And there is no chance that that number is other than 2. And the reason for that is it comes from a mathematical, infinitely precise concept or idea. So let me illustrate. The formula for the area of a triangle, it really comes from the formula for the area of a rectangle. So over here on the right, you see we've got a rectangle. And what we've done is we've drawn a diagonal like so. And what we've said really is that the area of a triangle is exactly 1/2 that of a rectangle. Notice that as an idea or a concept. There is no uncertainty. No one is going to argue that the area of the triangle is 1 over 2.1 of a rectangle or 1 over 1.9. That too is absolutely certain. It is theoretic. It's a theoretical construct. It's an absolute idea. And that's the beauty of mathematics. We can do that in mathematics, but it turns out science and physics and such deals in the real world. So that being said, we have the area of a rectangle is length times width, and we could redefine length and width as base times height. So then when we want the area of a triangle, of course, we're going to take 1/2 that. And that's where that 1/2 comes from. So knowing about the uncertainty associated with this number 1/2 depends on where the 1/2 comes from. So if we're going to look at the numbers that would be used in computing the area of a triangle, say the light gray one on the right, the 1/2, we know it without doubt, without a question, very precisely. But when we look at the base in this case, we know this is a scientific measurement. It was made by a scientist using a measuring device. And the convention, the convention we use is that the last digit is always where the uncertainty lies. It's always where the uncertainty lies. So this one in this case has 3 significant digits, the 7 being uncertain, that's where the uncertainty lies, and the height also has 3 significant digits, and the 9, where the 9 is where the uncertainty lies. So what that means then is that when we have a measurement, it is not an exact number. It has finite precision. In the case we've got here, they each have 3. So it has exactly 3 significant digits. Now, of course, when we perform a calculation, the calculations are based on those measurements. So it also is not exact. It also has finite precision and a finite number of significant digits. The last example or source of the numbers that we're going to deal with in the course are estimates, and we are going to save that for a later lesson.